So this kind of nervous feeling is really exciting. So from me, there's gonna be a space journey, and I call my project Push the Craft Faster every single time, and in a more complicated way, optimization for laser-propelled spacecraft for all launching times. And I am Yiluo from Concordia International School, Shanghai. My mentor is Qicheng Zhang. Let's begin. And so in our project, we're trying to use laser instead of fuel. And this is an artistic expression of sail on spacecraft. So you can imagine a boat with a sail and wind, except that now the wind is actually laser and photons. We use D-star laser, stands for directed energy solar targeting of asteroids and exploration. No comments on why R stands for exploration. Let's keep going. So when the source of propellant is laser, we get higher speed. To make sense of how fast that can be, well, here's one comparison. The farthest we went in the universe is the Voyager 1. It's launched in 1977 out of solar system at 2012, which means it took about 35 years. And compared to the speed of light, that's about 0.006%. That's, well, 0.006%. What if we can make it a lot faster? This is a simulation result for D-star 4. D-star 4 is just one of our laser system. And like among these, the craft mass varied from 1 kilograms to 10 to the 4th kilograms. And even the slowest one is 10 times faster than the Voyager. So everything just seems really cool. But what is the problem? So here is the problem. Time cost is overly sensitive over changes in starting time. This is a graph. This is a graph of time needed and the speed to get to a certain distance. So it's just something like we launch it today, how much time it took. We launch it tomorrow, how much time it took. And then we launch the day after that, how much time it takes. And then you just can see the graph is really kind of unpredictable. This is really a huge problem. So it's really hard to kind of launch it, because if we launch a day like later, the time cost is like really high, and it takes this really long, which is not optimized, I guess. And why that happens can be kind of well demonstrated in this animation. And the darker one inside is the laser orbit, and the lighter one outside is the craft orbit. You can see that here's a part that the orbits like almost overlapped. But you can see when they kind of arrive here, they're kind of like pretty far away from each other when the craft come back. So we really do want them to converge at this point where they're like closest. What do I mean by converge? Is just like they can kind of meet each other at this overlapped part. So maximum force can be added on to the craft, which means it'll just go faster. So yeah, the poor spacecraft here never really escaped the hands of human beings. And this is the effect of converge repeatedly. Like the craft is just like go around and goes away, pulled back by the Earth's gravity, but then it converges, so goes away really fast. So in our lab, what we did is that we make this optimizer. The optimizer, what it will do is that it will make the spacecraft and the laser converge at that point where I said that their orbit kind of overlap. And this is like the closest point. And this is the really simplest expression of how it works. We made the time that the craft need to get to that closest point, and the time that the laser need to get to that point, the same. Well, it's not the same. There will be a little bit difference because it will be like off a little bit, but that's why it's called optimizer, not perfecter. So we made this happen, and before I jump into the result, I was just say like it's really cool, but what is the significance of it? The optimizer will make the system more efficient. So which is just optimization at all launching time. That is my title. And it will reach out really far with less time needed, faster. So the goal of my project is try to minimize the time, cost, the duration to get to a certain point of this craft, and make the spacecraft and laser converge repeatedly, which sounds really romantic. Let me turn off the light so you can see this clearer. So These two are the animation like before we implanted the optimizer, and these two are after. And then you can see that at first it seems just like pretty much the same. And even this one actually will seem like a little bit better than this one. Let's see. Oh, it's a little bit slow. So you can see that this one seems like going a little bit further than this one with optimizer. However, if you look at it carefully, it's pulled back by the Earth's gravity. It's pulled back, it's going back, and this one already shows like a kind of better than this one because you got look at this, it's going away, and then it's going away, out of range, and this one's still orbiting the Earth. They all have like the same setting, initial setting, except that they're like this is. You can assume that it's like day one. This is like the second day that it's launched. You can see that after the optimizer, it's just really going further, while these two are still kind of orbiting the Earth, like really don't escape the Earth's gravity. Oh, all right, thank you. And this is just the orbital trajectory of two craft with same setting, but this one is without optimizer, this one's with optimizer. And you can see that it's just really going like a straight line and going really far away to this like really high. This is like 2 times 10 to the 6, and this one is still kind of orbiting the Earth and within a really smaller like range. And also this one, this result is a little bit not within like our initial goal, but the kind of effect is expected. So you can see after the optimizer, this is the change of time and speed over the change of laser power. So it's like if we push this hard, how much time it will take. If we push like harder, how much time it will take. And then we push even harder, how much time it will take. And in this graph, it's kind of clearer. Like it's pretty obvious that if we push it harder, the time cost will be like shorter. But in this one, before we implanted the optimizer, it's a little bit unpredictable, like a little bit not that clear as this one. And here, there is even like a blank, which means target distance not reached. However, how to use this optimizer is really critical. We need to use it like properly, and use it too many times within one simulation can actually mess up the results. So if you look at this comparison, the left one is still the one without optimizer, and the right one is still the one with optimizer. You can see at this part and this part comparing to here, this is flat and kind of low. I mean, so the time cost is like really short. But then with optimizer, it's kind of like, you know, high and like jumpy here. So in this case, without optimizer, it's actually better. So probably in our future development, we'll try to like add some inputs to try to make the optimizer work better. And this is just a list of the inputs we already do have, but we'll probably add on to this list in the future. And also, we'll try to find out the reason for this ineffectiveness of the optimizer. And if the statistic analysis will help, we'll probably use that as well. And finally, just acknowledgement, Qicheng Zhang, my awesome mentor, D-Star Lab, everyone's nice, UCSB Experimental Cosmology Group, long name, huge group. Ross, my TA, Linda Kim, Director of Research Mentorship Program of Summer Discovery, Concordia International School, Shanghai, my awesome high school, and my awesome family who sent me here. And also special thanks to Jilly, who's my roommate, gave me a lot of advice on this presentation. Thank you very much.